Hi, this is an example problem on satellite motion. Take a moment and read the problem. All right, so for satellite motion, we got a couple equations that we can always use to solve any of these type of problems. And one of them is one that you've seen already from kinematics of uniform circular motion. The other equation is one that we get when we apply Newton's second law to the case of a satellite in orbit about a central mass with a capital M as the large mass that the satellite is orbiting. So let's copy these two equations down. So we've copied down our two equations. We can see there's four variables shared between them. We've got V, we've got R, we've got T, and we've got M. G, capital G, is just Newton's constant for universal gravitation, which we can look up when we need it. Now, if you're going to solve a problem with a single satellite, then of course you can use these equations. In this problem, we actually have two satellites orbiting the same central mass. And so I'm going to go ahead and set this up by writing satellite 1 here. And I'll make a separate column for satellite 2. And I'm going to go ahead and write down for each of these variables. For the first satellite, we can write each of these four down. And I'll do the same thing for the second. So there we've gone ahead and written down the two satellites and the information we want to try to gather. If we can get any two of the variables for one of the satellites, then we can use one of the two equations to solve for any of the other information, since they each have three of the variables in them. Now, an important thing, notice that I did not write down for M subscripts 1 or 2. Why is that? Well, this is the same because they're both orbiting the same large body. So I've drawn a little picture of the two orbital trajectories and the central mass in the center. And we see that we're given a couple of the radii, right? So for the, let's say this is the first satellite, right? It's got R1, which is shorter, and the second satellite has a slightly larger radius. So R1 here, I'm going to call that the inner trajectory, right? So that is this one here. We'll go ahead and write that down. So we've got 5.26 times 10 to the 6th meters, whereas the other satellite has this radius, and so let's write that down, 8.60 times 10 to the 6th meters. And we're given one more number. Let's see what we got here. So back to the first satellite, we've given the speed. We can write that down. So we've got 1.7 times 10 to the 4th meters per second. Now we're asked, what is the orbital speed of the second satellite? We want to know what this is, right? Currently, I don't know enough information to solve for V2, right? I've only got one thing. However, over on the other side, we've got 1, 2 things. We're good to go. I could solve for T1. I could solve for M. Which one do I want to solve for? Clearly, I want to solve for M, because once I know what M is here, then I already know what it is there. Once I know what M is there, I know two things, and then I can solve for V2. All right, so let's go ahead and do that. Which equation do I want to choose to solve for big M from satellite 1? Well, it looks like we might want to do this one here because we know what V and R are equal to, and we can solve for M. We just look up G. So let's go ahead and write that down here. So I've written down the second equation, and we want to solve for M. Let's go ahead and do a little bit of algebra here to isolate the M term. And we find that M is equal to the speed squared times R1 all divided by G. And we're going to go ahead and put those numbers in and see what we get for M. So plugging in our numbers for satellite 1 and inserting into our calculator, we find out that the central mass that the satellites are orbiting, 2.278 times 10 to the 25th kilograms. It's a big number, but that's to be expected for a planet. And now that we know what the mass is, right, it's the same for both. We've got two knowns in the column for satellite 2, and we can go ahead and solve for this. So which equation do we want to use? Well, we know the value of v of r2 and m, so we can use the second equation again. So let's go ahead and write that one down. v2 squared is equal to gm over r2. And we just need to go ahead and plug in our numbers. Well, I guess before we do that, we should probably take the square root of both sides. Speeds are positive, take the positive root. So v2 is going to be equal to square root of gm divided by r2. Let's go ahead and plug our numbers in. So we plugged in the numbers, and this comes out to a value of 1.33 times 10 to the 4th meters per second. And so that is the speed of the second satellite. Notice that the second satellite being further away, less gravitational acceleration, is going to have a lower speed than is the closer satellite.